this particular table, we will see how bivariate data can be analyzed. And as Charles was talking about the hypothesis, you know null hypothesis and you know alternate hypothesis, right? So there is a difference in the nature of the hypothesis also. So the hypothesis can be framed in order to check whether a particular variable A influences another variable B or has an association with another variable B, or it can just talk about the magnitude or the tendency of one single variable or compare it among two different groups. So when we're talking about the difference between the groups, then that hypothesis is called as hypothesis of difference. So depending upon whether the hypothesis is hypothesis of difference or hypothesis of association, the way in which we decide what test has to be conducted will differ. Anova is a means to compare. Anova is a means to compare the means of a particular group. So supposing, let's say I have group A and group B, that is male and female. I want to check out if the height of 10th grade girls and 10th grade boys are same or not. Now that is an hypothesis, or that is an hypothesis of difference that we are talking about. So here, when you're trying to check the hypothesis of difference, again, you have to see whether the particular data that you have with you, is it a parametric data or is it a non-parametric data? Can anyone tell me what is the difference between parametric and non-parametric? Okay. If there are no answers, let me move forward. Parametric data is your data follows normal distribution. Okay, your data follows normal distribution. So why should a data follow normal distribution? When my data follows a normal distribution, then I have a possibility of doing certain tests. If my data does not follow normal distribution, then certain tests cannot be conducted because every test has certain assumptions. So only if it matches certain criteria, I can do that particular test. Otherwise, I cannot do the test. So in this case, for Anova, your data should be normal distribution. If your data is not a normal distribution data, then you cannot do Anova, and in place of Anova, you have to do some other test. Okay. So next, coming to this is we are talking about bivariate data. So after you check the parametric nature or the non-parametric nature, I have to see whether the sample is a paired sample or an independent sample. So what is the difference between independent sample and paired sample? So supposing I gave an example about boys and girls. Boys and girls are two independent groups. A person from boy cannot be a part of B. So that is why we call these two groups as independent groups. Whereas dependent or paired means the same group of people are there in the two groups. So for example, let's say I want to check the effectiveness of trials or effectiveness of the coaching in a particular gym. So I am selecting 40 people before they start the training, and I take their weights. After 40 days, again I select the 40 people and again I check the weight. So here the people are the same. Okay, the people are the same. So it is a dependent sample. So another word for dependent sample is also called as paired sample. So in the case of bivariate data, if your data is parametric and if your sample is independent sample, then you have to do an independent sample t-test. Whereas if your data is a paired data, then you have to do a paired sample t-test. I'm not going into the other part because that is out of our purview. You're just going to understand t-test and then move forward with the Anova. So next, coming to multivariate data. So in multivariate data also, you can have hypothesis of difference, you can have hypothesis of association. So when you're going for hypothesis of difference, you have to check whether your data follows parametric nature or not. So when your data is parametric, then you go in for Anova. Whereas if your data is non-parametric, you have to do another equivalent test, which is called as Kruskal-Wallis test. So in Kruskal-Wallis, you do not have any kind of requirement. In Kruskal-Wallis test, you don't have any kind of requirement that your data should be parametric data or normally distributed data. So this is just an identification for you to understand how to decide what test you're supposed to do. So coming now to our topic, Anova. The Anova, ANOVA, stands for Analysis of Variance. So for a multivariate data, multivariate data means more than two variables the data should have. For a multivariate data, when you are trying to find out if there is a difference between the means of a particular variable, okay, if there is a difference in the means of a particular variable among more than two groups, okay, among more than two or more groups, then it is called as Anova. So the basic condition is it should be more than two, there should be more than two groups. The dependent variable should be a continuous data or metric data. And the independent variable, that is the groups, should be categorical in nature. So if you see the hypothesis for Anova, it is trying to test the means, or it is trying to test the equality of means of more than two groups. So what is the meaning of a group? See, for example, in your questionnaire, you ask questions like gender. Okay, so earlier we used to ask only male, female. Now we are asking male, female, other. So when you have three groups, for that also you can do Anova, provided somebody has ticked on other. Or you might have educational qualification, or you might have different types of schools that they have attended, or different types of organizations where they are working. So you have different categories, let's say like software, KPO, then manufacturing, then government sector. So these are four different groups. Okay, now you want to find out the job satisfaction mean between the four groups. Are they equal or not? Okay, are they equal or not? So for that, you have to do an Anova test. So Anova is thought as an extension of an independent sample t-test. So independent sample t-test you do for two groups. When there are more than two groups, you do an Anova. Okay, so the hypothesis will be, the null hypothesis will be mu1 is equal to mu2 is equal to mu3 is equal to mu4. So in my example, job satisfaction of people among the four groups, are they equal or not? So null hypothesis always assumes they are equal. Alternate hypothesis assumes they are, so even one can be different from the other. As I told you, every test has its own assumptions. Okay, so the dependent variable, that is the job satisfaction that we are taking, it should be either an interval scale or a ratio scale. Second is, I have taken different organizations, right? So that is an independent variable that should be categorical and it should be independent in nature. Independent means a person from software should not be in manufacturing. A person from government sector should not come under IT sector. So this is the independence nature, and minimum more than two groups should be there. That is a condition. Second is you should have independence of observation, which means that one observation does not influence the other. Okay, one observation does not influence the other. Giving you an example, what is the meaning? If I toss a coin, my first whatever answer I get, does it have an influence on the second toss? No, right? So that is called as independence of observation. There should be no significant outliers, simply meaning that your data should be normally distributed. Okay, if your data is normally distributed, you will not have any outliers. The next is the dependent variable should be normally distributed for each category of the independent variable. Next is there should be homogeneity of variances. Now, this homogeneity of variance is a very specific condition for Anova. Why you need to have it is when I divide the groups, let's say government sector, IT sector, etc. In each group, the variance that is there should not be very much different from the other groups. When the variance level is highly different between the different groups, then your results will not be reliable. So it is important that you should have homogeneity of variance, and for which we do a test along with Anova, which is called as test of Levin, Levene, Levin's test. And based on that, I will do it when we are interpreting the test. So following the Anova test, you have post-hoc test. So post-hoc test helps to identify which pair of the population means are significantly different. Okay, post-hoc test helps to identify which pair of population means are significantly different from the other. So in the earlier ANOVA, it will only tell you there is a significant difference, there is not a significant difference, or whether the groups are all equal or there is some difference. That's all it will tell you. But post-hoc will tell you, supposing I have 4 groups, group 1 is different from group C, group 1 is different from group 4. Group 2 is different from group 3. So that difference, which is difference, is given by post hoc test. So this is one more flow chart which you can use to decide how to run ANOVA. So the basic conditions are your observation should be independent. There should be a normality condition which should be satisfied. Homogeneity of variance also should be satisfied. So these are the conditions. Am I audible?
Yes, ma'am.
Okay, right. Right. So here we are going to do a small test, which is called as a depression.sav file. So in this, the data or the content that is given here is the ID is given. ID is employee ID is given. Gender, male or female. Birth date of a particular individual is given. Then there is a score, which is called as depression score of a particular patient. Okay, BDI, it's the Beck's depression inventory score. Then you have the group based on the score. They are making you into different groups, so that is a score. And the last one is what is the treatment given to the particular patient. So based on that, we will do one ANOVA. So 100 participants suffering from depression. This is the details regarding the particular problem. 100 participants suffering from depression. They divided into 4 groups of 25 each. Each group was given a different medicine. After 4 weeks, participants filled out the Beck's depression inventory questionnaire. And the research question here is there a difference in the mean BDI scores among the 4 medicines given? Okay, they are giving 4 different types of medicines. So based upon the medicine, they are segregating the groups. So after the treatment, they want to find out, has there been a reduction in the BDI score? Okay, so that is what they want to find out. So the null hypothesis here is there is no difference in means of BDI scores among the 4 medicines. M1 equal to M2 equal to M3 equal to M4. Okay, now quickly I will tell you how to run analyze, compare means, one way ANOVA we should go. Then we will go on to putting the score on Beck's depression inventory in the dependent. Or shall I skip this and directly go to SPSS? I think that's better, right? Okay. So we can go into SPSS. So all of you can open the ANOVA file, save. Okay. Yes. Is the file visible?
Yes.
Okay, right. So in this file, I need to zoom it up. We have ID, gender, birth date, BDI group, and medicine. So there are 4 different types of medicine. If you want to find out what are the different types of medicines, you can go to variable view. Then you can see this. So 1 is none, 2 is placebo, 3 is homeopathic, 4 is pharmaceutical. So these are the 4 medicines administered for the particular groups. Now how to run an ANOVA? Go to analyze, compare means, one-way ANOVA. Analyze, compare means, one-way ANOVA. We have gone to analyze, compare means one-way ANOVA. One-way ANOVA window box opens. Then here there is a box separately for dependent list and there is a box separately for factor. So here our dependent list is, what is our list? What is our dependent variable? It is the depression score, correct? So score on Beck's depression inventory should go into the dependent list. So based on the medicines administered, we are trying to see if there is a difference. So medicine administered should go into the factor. Okay. Score on Beck's depression inventory should go to the dependent list and medicine administered should go into the factor. Then going on to post hoc. So what is post hoc? I told you, to find out which particular treatment is different from the other, you require a post hoc test. So here there is something called as a TUKEY, TUKEY, in the second column. Okay, in the second column, second row, you have TUKEY. So just click on TUKEY and say continue. Then when you go into your options window, you click on descriptive homogeneity of variance test. Okay, homogeneity of variance test. Say continue, say okay. So are you fine? Do you want me to repeat it again?
No, ma'am, it's fine.
Right. Is my output window visible?
No, ma'am.
All right. Okay, 1 minute. Yeah. Is it visible now?
Yes, ma'am.
Right. So see here, this is the one-way ANOVA here. In the one-way ANOVA, the first table is a descriptive table. It shows you under each different treatment, medicine treatment, what is the number of people. N stands for that. Mean stands for what is the depression score after the particular treatment was given. For none, it is very high. For pharmaceutical, it is quite low, 26.88. So these 2 columns are very important from the first table, which will help you to interpret. Second table is test of homogeneity of variance. See, when your p-value is less than 0.05, what is the interpretation? Can anyone tell me? When your p-value is less than 0.05, what is the interpretation?
We reject the null hypothesis.
Yeah, you reject the null hypothesis and accept the alternate hypothesis. What is your null hypothesis usually? Your null hypothesis is there is no significant difference. Okay, there is no significant difference. There is no significant difference. Okay, that is your null hypothesis. So here, your p-value in the second table, homogeneity of variance table, is greater than 0.05. So what do you mean by that? It means that your null hypothesis should be accepted. So one of the main assumption in ANOVA is that among the variance groups, there should be homogeneity of variance. Correct, which means that the variance should be same across the groups. So here, if your p-value is greater than 0.05, it means that the variance is same across the groups. Okay, so one assumption is satisfied. Okay, one assumption is satisfied. That is why we do test of homogeneity variance. Next, coming to the next table, that is Anova table. Here, the significant value is 0.000. So it is less than 0.01. So if it is less than 0.01 at 99% confidence level, we can say that there is a significant difference among the various treatments in the means of the depression score. Correct? So you understand the difference in the test of homogeneity of variance, significant value should be greater than 0.05. In your ANOVA table, the significant value should be lesser than 0.05. Then there is a significant difference. If there is no significant difference, if it is greater than 0.05, it means that all the 4 treatments are giving you the same results. Okay? Any doubts, any clarifications? The first ANOVA I will do in detail, then the remaining ones I will just rush through. Is it fine? Let me move forward. Okay, so next is the post-hoc test. See, in this post-hoc test, how to interpret this table? So you see here in the first column, you have 2 subdivisions. So they are comparing none with placebo homeopathic pharmaceutical. Second, they are comparing placebo with a non-homeopathic pharmaceutical. Like that, each medicine they are comparing with the remaining 3. So there will be some kind of repetition. So to see whether these 2 are significantly different or not, you have to see the 4th column. So in the 4th column, you find that 0.003, 0.008, 0.000. So all these are significant, which means that none is completely different from all the 3. Pharmaceutical is completely different from all the 3. Whereas homeopathic and placebo, they are similar to each other. Okay, so this is the interpretation based on the significant value. So you have to see the 4th column and then interpret with the first column, what and what. So the 2 keys test also shows you that among the 4 medicines, first one is none. So none is different, pharmaceutical is different, and placebo and homeopathic are more or less same. So this is how you should interpret an ANOVA table. Is that clear? Any doubts, any clarifications? Right. So let me.
Could you mention the degrees of freedom?
Okay. See, the degrees of freedom, what you should take is, now you have to take the error. The error is 96 and 3. Okay. Between groups you have to take. That is what we're trying to find out. Between the groups, is there a significant difference? So when you're writing, you have to write the F. Okay, the F value of degrees of freedom 3, 96 is equal to 20.730, where significant value P is equal to or less than 0.001. Okay, right. So this is how you write the interpretation. So I will stop sharing this and I will go back to my I will close some output tables. Yeah. So we have finished. I will show you how to interpret the table. See, this is how you should interpret the table. There was a statistically significant difference between groups as determined by one-way ANOVA. So the F value of the degrees of freedom 3, 96 is equal to 20.732, where P is lesser than 0.001. And then you have to talk about your Q-keys test, which is significant from what. Okay, now whether it is a one-way ANOVA or two-way ANOVA is determined by the number of independent variables used. Okay, the more the independent variable used, the name will change. So you can have one way, which means one independent variable is used, two way, where two independent variables are used. N number of independent variables, when you use it, it is called as factorial ANOVA. Okay, so we are going to do a two-way ANOVA with interaction effect. What is the meaning of interaction? There is a gender. Okay, so there is a gender effect. Now, the same test that we used earlier, we will use the same thing again. So these are the assumptions. More or less, all are the same assumptions that we had. So here, for a two-way ANOVA test, the question is, we use the Beck's depression inventory score. Same thing we will use again. Now we will try not only with medicines, we will also add the gender element to it. Okay, we will also add the gender element. So the basis goes like this. When it is a two-way ANOVA, or when you are not doing a one-way ANOVA, if you have to perform ANOVA, you have to go into general linear model. So analyze general linear model, and depending upon whether your dependent variable is one or many, you use univariate or multivariate. So this is how you should perform the test. So we have to, we will do it there directly. Okay. So this is the data. Is my SPSS screen visible? ANOVA file?
Yes, ma'am.
Right. So analyze general linear model. We'll go into univariate. And then the dependent variable is like before diagnosis, no, before score on Beck's depression inventory. Okay, medicine administered is a fixed factor. Along with medicine, we are going into gender. Okay, along with medicine, we are going into gender. Now go into contrast. I'm sorry, go into plots. So here you put the gender on the horizontal axis, medicine on the separate lines, then say add. So an interaction effect or an interaction model will get added. So there is medicine, the effect of medicine on the patient. There is an effect whether he is a male or female also, which influences the depression score. So we are trying to find out an interaction between gender and medicine. Okay, then continue. Go to post hoc. Post hoc test, we are going to do it for medicine administered. Click on Q key, say continue. Then go into options. Here display means for medicine. Descriptive statistics, estimate of effects, homogeneity. These are the three common ones that we usually choose. Descriptive statistics, estimates of effect size, and homogeneity. Say continue and then say okay. Okay, I'll stop sharing. I will share the output. Yeah, so you got the file, you got the output on your screen?
Yes, ma'am.
Right. So here it shows the first table shows you how many number of people are there in a particular group. So for male and female, how much it is there. For gender, how much it is there. The second table, it gives you a descriptive statistics based upon none for male, how much, for female, how much. So you see here itself, the depression score for females seem to be slightly higher when compared to males, except for the group which has used pharmaceutical medicine. Clear? So the depression score seems to be high for females when compared to males. That is one interpretation that you will get seeing the means. Okay. Levin's test of equality is also satisfied because you have a significant value 0.7, which is greater than 0.05. So it is satisfying that particular assumption also. Next, coming to, you have to see here medicine into gender. So come to the table, test of between subject effect. Okay, test of between subjects effect. You have to look it into the row medicine into gender. Okay, medicine into gender. So medicine into gender is 567. That is, see the significant value for medicine into gender. So when medicine into gender is significant, 0.002. What is the interpretation? The interpretation is that there is a significant influence of the combined effect of both, that is the medicine and the gender on the patients. Okay, so it has a combined effect, so that is called as interaction effect. Whenever you have interaction effect, or when your interaction effect is significant, then you should not go in for the mains study. You should go in for a simple effect study. How to do a simple effect study? So we know that gender is influencing, correct? We know that gender is influencing. So I am going to split my data based upon the gender. Okay, I'm going to split my data based upon the gender into male and female. So how to do that? Go into data, split file, click on gender, compare groups you click, and then change it to gender. Okay, so you're trying to divide the gender into male and female groups. Now you're going to run the same test again. So it will show you two different tables for male, two tables, one for male, one for female. So go to analyze, general linear model, univariate. So all will remain the same. Say click on OK. So you see here, every table will have a difference between male and female. So it will show you. So when it shows you this, you see the Levin's test also is satisfied. The test of, is my output visible, right? My output is visible.
Yes. Yes.
Okay. So the test of between subject effect is also shown for male separately, female separately. So it shows here in this particular table, you see it shows the combined effect, interaction effect is significant for both male, also for females. In the post-hoc test, now come to the post-hoc test. In the post-hoc test, you see when you see males, okay, when you see males, only none and pharmaceutical are significant. Okay, none and pharmaceutical are significant, which means that there is a significant difference between no medicine and pharmaceutical medicine. Whereas if you take the females, you will find all of them are significant. All the groups are significantly different from each other, except for placebo and homeopathic. Okay, so whenever you find the interaction effect, you have to split the file based upon the particular data and then group it separately, and then based on that you will be able to interpret the data. So this is how you should do the particular table. You see there is an interaction between the second one, placebo and homeopathic, which means that they are more or less the same. Right. So I will go back again to my into my PowerPoint file. So all these are files. I've also put it into PowerPoint, which I will share it with you, so that you will be able to work it out. You can retry, work it out. If you get anywhere stuck, also it will be able to guide you how to move forward. Since you have the data files, it will be easy for you to work. So next is supposing there is no interaction. Okay, supposing there is no interaction. So how do I interpret? So there is another small test or a small case. So there is people are working and they're also dieting. You're going to see how 3 exercise levels and 3 different diets, how are they influencing around 180 participants. Okay, so in case, now see this particular test of between subject effect, we always have to see diet into exercise. When you see the diet into exercise, the significant value is greater than 0.05. So when it is greater than 0.05, it means that the null hypothesis is accepted. What is null hypothesis? There is no significant difference between the different groups. So in that case, you have to see the previous 2 rows, that is the diet row and the exercise row. So the diets have a significant influence, exercise has a significant influence, but the combined effect is not there. Okay, the combined effect is not there. So this is how you should interpret this particular table. So then based on that, see the next table. Here they are trying to see in exercise, you find that difference between none and 30 is not there. None and 60 is there. 30 and 60 is there. Okay. So that is how you should interpret the particular table. So important tables for Anova analysis is for assumption Levin's test. Then you have to look at the within group test of between subjects effect or between groups. The next is post hoc test or multiple comparison test. Okay. Now coming to Mancova. What is Mancova? Theoretically, we will do all this, then we will practically work there. What is Mancova? Mancova is multiple analysis of variance, which means that I am running multiple Anova. Which means that instead of one dependent variable, I am having multiple dependent variables. Okay, I am having multiple dependent variables. That is called as Mancova.
Excuse me, ma'am.
Yes.
I want to ask one question.
Yeah.
In our previous table where diet into exercise, yes, ma'am. In this, no, ma'am. Before this, yeah, where it is 0.444 significant. So it is above the 0.005 level.
Yeah.
And our null hypothesis is getting rejected by this.
Null hypothesis is accepted.
Accepted by this.
Never, whenever it is greater than 0.05, null hypothesis is accepted.
Okay, so there is no interaction between diet and exercise.
There is no interaction between diet and exercise.
Okay, thank you.
Okay, so what is the advantage of Mancova is that at one time itself, you will be able to run multiple Anova. Second thing is, it is said that if I run Mancova, I will be able to reduce the type 1 error. What is type 1 error? See, a researcher, when a particular hypothesis is true, okay, when a particular hypothesis is true, he should accept it. Instead of accepting it, he is rejecting the null hypothesis. So when he is doing a mistake like that, that is called as type 1 error. And this particular Mancova is said to reduce the type 1 error. Mancova, since you are having multiple Anova, it should be naturally complicated. Okay, it cannot be simple. It is naturally complicated. And because you're having more number of dependent variables, you should also see the dependent variables are not correlated with each other. They should be free of each other. So this non-collinearity also has to be satisfied. Okay, non-collinearity also has to be satisfied. So these are the assumptions. So most of them are the same like previous. The last one you can check, it is called as multi-collinearity should not be there. So that is one add-on. Now we are going to take another file and work out. I will just run through it and then we will finally run all the three together. Mancova. So this is about Mancova. Next is okay. Next is Ancova. Ancova is when there is a covariance in added to an Anova. What is a covariance? See, dependent variable, another dependent variable or another continuous scale which is existing, but you're trying to control its influence on the dependent variable. Let's take like this, okay. See, supposing I'm dieting, okay, and currently I am 120 kilo, okay, 120 kilo, or I'm dieting or I'm exercising, it could be anything. So supposing I'm around 120 or 130 kgs, if I'm sincerely dieting and sincerely exercising, in the first 1 month, I will reduce at least 20 kgs. Correct? I will reduce at least 20 kgs. Supposing my weight is currently around 65, which is very close to my ideal weight. How much ever I diet or how much ever I exercise, from 65, probably I will come to 63 or 62 or 64. I cannot go beyond that. So you find that your previous weight has an influence on what your future weight is going to be after the exercise. Okay, so in this case, what is an covariance? The covariance is the previous weight of yours. So without trying to have the influence of the previous weight, I want to see what is the effect of exercise or effect of dieting on the future weight. That is why you have to use an Ancova. So here your previous weight is an covariance which is controlled. Okay, it is a covariance which is controlled, and they are trying to find out the impact of the exercise and diet on the future weight. Is it clear? Right. So this is why Ancova has to be done. So in the case of Ancova, it is like doing a normal Anova. Only thing is, add on, there will be one more table or one more box, which is called as covariance box. We'll do another test for that. So the test is, when I'm going there, I will tell you. The last one is Mancova. So what is Mancova? Ancova is, you're using one dependent variable, you're using one covariate, and you're trying to use one independent variable or two independent variables. In the case of Mancova, you use all multiples. You can use two covariates, you can use two independent variables, you can use two dependent variables, or even more. So you are having more number of independent variables, more number of dependent variables, but we are trying to control the covariate. Okay, you're trying to control the covariate. That is called as Mancova. Okay, right. So we will slowly. These are the assumptions. So apart from homogeneity of variance, covariance, you should also check that the dependent variables have a linear relationship with the covariates. The dependent variables have a linear relationship with the independent variables. So all the groups should have normality. All the individual groups should have normality. All that has to be checked. So we will do the test one by one. So I will stop here and I will go share and go. Okay, I will work on Mancova first. Mancova is same as an Anova. Only thing is my SPSS screen visible to all of you?
Yes, ma'am.
Right. Thank you. Okay, so we have job category, we have department. One minute, my system has become slow. I'll just close unwanted windows. Right. Data set for Mancova should be visible to you people now. So I am going to do analyze general linear model. Since Mancova talks about multiple Anova, I have to go into multivariate. Okay, I have to go into multivariate. So the dependent variables here, okay, what are the different types of variables that we are going to study is salary, increment, employee satisfaction. These are dependent variables. Salary, increment, employee satisfaction are dependent variables. I'm going to use the job category as the fixed factor. Okay, job category as the fixed factor. So I'll put all the three here in the dependent. Job category as the fixed factor. Go into plots. Job category I'll put in horizontal. Add. Continue. Post hoc. Job category. Few key. Continue. Options. Same way, descriptive, estimate of effect, and homogeneity test. Continue and say okay. I'm just slightly rushing through due to paucity of time. Is my output screen visible?
No, ma'am.
Okay. Now?
Yes.
Okay, right. So this is the interpretation table. So first you will have a descriptive statistics like all. So here it is trying to divide the different job category based on the salary and increment and employee satisfaction. It is giving you the means. So when you see the means, it is an indication to you. Okay. So you see the means of salary, you find all the four are slightly different from each other. Probably two, I mean, all the three are different from each other, 39, 47, 57. Whereas increment, you see, all of them are more or less getting the same kind of increment, three groups. Employee satisfaction also, more or less, they are having the same kind of score. Okay, so next is, remember, we said that there is a test of equality. Okay, so we used to do the Levin's test. The another test is for covariance matrices. Box test. So here also your significant value should be greater than 0.05. So in this particular data set, it is not satisfying that particular condition. So if it is not satisfying that particular condition, you cannot move forward. But for the sake of explanation, I am going to go forward. So when you go to multivariate test, we have to look at the Wilks lambda. Okay, Wilks lambda for job category. Okay, Wilks lambda for job category, we have to see the F value is 72.455. Then the significant value is less than 0.05. So hence it is significant. What is significant? The job category is different from one another. Okay, the job category is different from one another. Next, we will go down and see in this salary of the employee is less than 0.05. So which means that among the various job category, the salary is different among them. Whereas increment of the employee, the P value is greater than 0.05. So there is no significant difference in terms of increment of the employee. For employee satisfaction also, there is no significant difference. So the only difference that is found in the job category is because of the salary. So next coming to test of between thing. So this job category with the salary is significant. See the fourth row and the significant column. Okay, so the job category is significant in terms of the salary of the employee. So they are different from each other. So coming here, salary of the employee with this. So it says this is the mean, different mean that we already saw. Seeing the post hoc test. So salary of the employee with group 1. So all the groups are significantly different from each other. Okay, all the groups are significantly different from each other. So in your ANOVA table, the important area for your analysis is you have to look at the first mean table to understand. Second, the Levin's table or the M plot table to find out whether the assumption is satisfied. Third is you have to look at the post hoc test, and then you have to look at the ANOVA table or the Wilks lambda square, which tries to give you an understanding about the particular significant influence. Okay. So this is how you have to do the particular test. Right. So next, just a minute. Okay, so this is how the interpretation has to be done. Now I will close this. Mancova is completed. So next I will go into Ancova. So what is Mancova? Along with an independent variable influence on the dependent variable, we are adding the covariate. So we are trying to control the effect of covariate and find out the influence. So in this particular data set, we have sex, we have birthday of a particular individual, the pre-diastolic pressure. So when you check the blood pressure of an individual, you have diastole and you have systolic numbers. Okay, so the pre-diastolic is before the treatment was given, pre-systolic is before the treatment was given, whereas post is after the treatment. So I am going to take the impact of treatment on post-diastolic pressure, keeping the pre-diastolic pressure level constant or covariate. Okay, so how do I do that? Go to analyze, general linear model, univariate. So this is before treatment. Before treatment, I am going to put it under covariate. Treatment is the fixed factor. Then diastolic blood pressure after treatment is a dependent variable. Understood? So I am trying to see the effectiveness of treatment on the post-diastolic blood pressure. What I am trying to keep it as constant or trying to hide its effect is the pre-diastolic blood pressure. Okay, pre-diastolic blood pressure. Same way, go to plots, treatment. Options. Say okay. My output file is visible.
No, ma'am.
Okay. Now,
Yes, ma'am.
right. So this is what we are trying to understand. We are taking four different type of medicine levels, and the first table shows you the four treatments. Second one shows you what are the means of the particular treatment. The third one, Levin's test is satisfied because it is greater than 0.05. Next, coming to test of between test. So here we have to see the treatment. So the treatment is significant. Okay, the treatment is significant. Okay, so the treatment is significant. So with the new medicine, the diastolic blood pressure level as, so the diastolic blood pressure covariates is 100.404. That is kept as constant. That is the earlier score. Keeping that as constant, they are trying to see how the medicine has tried to bring down the diastolic blood pressure in the particular individual. So this is the interpretation. This is the interpretation of the particular table. You have to see the treatment. You have to see the F value 8.194. The significant value is less than 0.05. Okay, and here your degrees of freedom will be 3,115 error term. Okay, so this is how the interpretation has to be done for this particular table. So this is about Ancova. Now we are going for Mancova. So this is the table here. So in Mancova, what is the significance? You can have more number of independent variables. You can have more number of dependent variables. You can also have more number of covariates. Okay, so sales 1, sales 2, sales 3, sales 4 are the four different types of sales stores and the sales that is happening in the particular stores. There are four different stores or four different sales are happening in each stores. So sales 1, sales 2, sales 3, sales 4 are those figures. The next is the age of the stores is given in the form of age location. Okay, the age of the stores is given in the form of age location. Then promotion in the form of what is the strategy that they are using for promotion. Promotion 1, promotion 2, promotion 3. So you are taking the age location as a covariate. You're taking promotion as a categorical fixed factor. Sales 1, sales 2, sales 3, sales 4 as four different dependent variables. So go to analyze, general linear model, multivariate. Okay. So all the sales, I'm going to put in the dependent variable. Fixed factor is promotion. Age of the store location. So how many years this particular store has been functioning. So that is also a continuous variable or a metric variable. So that is coming under covariates. So plots, promotion, add, continue. Okay, so this is the interpretation output table here given. Now you see here, we have to first check out the first table shows you for each promotion, what is the number of stores that have been taken for the study. Then it shows you descriptive statistics for sales 1 for strategy A, what has been the mean. So you can also compare which strategy is actually doing well, which strategy is not doing well across different sales. Then the box test plot is also satisfied because it is greater than 0.05. Then coming to the multivariate test, you have to look at the Wilks lambda for promotion, whichever is your categorical variable, for that you have to see. So promotion, second line, Wilks lambda, see the significant value, it is significant. The F value is equal to 4.025. Okay, 4.025. So F is this value, Wilks lambda value is 0.786, and it is also significant. So Levin's test is also satisfying all the conditions because everywhere it is greater than 0.05. Then you have to go into your promotion thing and then check the p-value. All the p-value is significant. So it says promotion has a significant influence on sales 1, sales 2, sales 3, and sales 4. Whereas age, location does not have any significant influence. Okay, age, location does not have any effect. So that effect is not taken into consideration here. Okay, so this is how. So for each sales, we are given a diagram to show how strategy B, what has been the sales, strategy A, what has been the sales. So more or less you find all are having a V-shaped curve, which shows that strategy B seems to be a failure, strategy A and C is good. Okay, so this is how the interpretation should go. I'm going back to my PowerPoint file. Okay. So this is how I've shown. Now see here, check the Wilks lambda row. Effect size is called as partial ETA square. So in all your tables where you saw the Wilks lambda, next to that F value and significant value, you found a partial ETA value. So that also has to be written as partial square value. Okay, so there is a statistically significant difference between the promotions on the combined dependent variables after controlling for age location of the stores. So this 8 and 252 are the error terms, are the degrees of freedom of location or of promotion and error. Then 4.025 is the F value, Wilks value is 0.786. So this is how the interpretation has to be written. I know I've been slightly fast because there was so much to cover and I wanted to complete it on time. So is there any doubts? Not only in this, any other basic doubt also, if you have, you can ask. If I know, I will answer. Okay, so if there are no doubts, thank you very much for your patient listening. You can always reach me on my mail ID or you can reach me on my mobile number. So in case you have any doubts or any clarifications or you need any help for your PhD thesis, I would be willing to help. Bye. See you all.
Thank you, ma'am.
Yeah.
Thank you.